Okay, so now the observer sees a current flowing through the rod, and because of this, whenever we know that whenever we have a current flow, we have a magnetic field. So just by virtue of shifting the reference frame from one that isn't moving with respect to the charge distributions to one that is, now we go from a situation where we didn't have a magnetic field to one where we do have a magnetic field. Okay, so now from Ampere's law, what we're trying to do here, where we're working towards, is to compare the acceleration in these two reference frames. Okay, so from Ampere's law, we get that an expression that relates the magnetic field with the current. Okay, I is the current, and therefore just solve for the magnetic field. We're just doing algebra. Is equal to the charge density times the velocity, which is the current, divided by 2 pi divided by the distance y. Okay? So in this reference frame where we have a magnetic field and an electric field, remember the electric field is still there even though we're now in a moving reference frame, moving relative to the charge distribution. We have to consider both the electric and magnetic parts of the Lorentz force. Okay, so we have the charge times the electric field, which is what we had before, and now we have this other part. Okay, this comes from the current, the velocity cross product with the magnetic field. So if we plug in for this, okay, we get, just from above, we get charge times the charge density in the rod, I guess just doing algebra, okay, so we're just plugging in for the electric field part of the Lorentz force, which is the same as what we had before, and then there's this new part which comes from over here, calculating the magnetic field. Okay, so let's just simplify. Okay, so this is equal to oops, I'm sorry, I jumped the gun here. Times 1 minus, okay, so finally this leads to an acceleration which is equal to the charge times the charge density, the charge of the particle times the charge density of the rod, divided by 2 pi epsilon naught, the distance, mass, and okay, so now we've simplified this, and we recognize that this factor out front is actually just the acceleration which we calculated in the reference frame, which is at rest with respect to which is at rest with respect to the charge distribution. So now we have a relationship between A prime, we have a relationship between A prime and A. Okay? And we see that in general they're not equivalent. Unless the velocity of the observer, v, is 0, then in general the accelerations measured in these two reference frames are not the same. So the two observers do not agree.